Hey, what's going on, guys? Kins here. There are two major ways of implementing the attacks regarding whatever chess piece on board when it comes to either generating moves or implementing the is-square attack function to determine whether the current given square is attacked by the opposite side or not. So the first way is calculating the attacks on the fly, which is slower and well, this is just slower, and but that's the exact way, the exact approach that is taken within the array-based boards, in those chess engines that consider array-based board representation. But when it comes to bitboard, even though that we still can use this on-the-fly attacks calculation, still people consider pre-calculated attacks to be stored. Well, so just the idea is to initialize the array of bitboards containing the pre-calculated attacks for every single given piece on board. So the matter of answering the question whether the square attacked or not, or where the piece is about to go, is just a matter of a lookup to the specific table that has the already pre-calculated information regarding the attacks for every single given piece on a chessboard. And believe me, just trust me, it's far easier to show and implement rather than to explain with this to me. So now I'll try to give a visual example of what exactly we're supposed to be doing in this video, and then we'll implement this in C programming language. And I'm trying to keep this bitboard tutorial series in a format of highlights, so we're not kind of developing a bitboard chess engine or move generator from scratch. Instead, I'm just trying to highlight some most important techniques regarding bitboards, and here is one of the most essential parts regarding the bitboards in general. So we'll also go through not only the pawns like in this video, but also through the knights and kings, like all the leaper pieces, and also we'll go through the slider pieces, which is absolutely fantastic experience for those of you who has never been doing this before, because generating moves or generating attacks for sliding pieces is the matter of discussion of years, basically, in forums like talkchess.com. So without further ado, let me just try to stop my explanation. So let's consider that we have, sorry, not the king, let's consider we have a pawn on a square d4. So white is here, black is here. So pawn is going upwards like this. So it can capture either here or here. And if we calculate the offset, this would be respectively 7 and 9 squares offset, depending on board and the n is obviously, but that doesn't matter. Anyway, this would be either plus or minus 7 or 9 squares offset to calculate the index of the current given square the pawn is going to. And if in case of the array-based board representation, we were just adding or subtracting this subset, this offset, in order to calculate the target square, target index in the board array. In case of bitboards, we can just use this offset to shift the bit on the appropriate index, and that's how it's done basically. So the idea is that we need to have up to 64 bitboards stored as an array, and we need 64 bitboards for white pawns and 64 bitboards for black pawns, respectively. And now let me just try to show how this bitboard is going to look like. So say we have the pawn here, so this is one of the bitboards, and another bitboard will have the pawn here and here. So the white pawn represents the bit that is set up on the white pawn bitboard, attack bitboard, and the black pawn is representing the squares that are attacked by this knight. So just trying to show this visually. So we will have a bitboard, an attack bitboard for white pawns, where white pawn would occupy every single square possible, even though pawns won't be really on the first rank and on the 8th rank, because on the first rank is just impossible due to the rules of the game of chess, and on this rank, on this 8th rank, it would be queen or whatever. It won't be a pawn anymore. But still, from the bitboard attacks perspective, we need to initialize the pawns on whatever square. So say here, we can capture here, it's off board, but we can capture here. Now if we just put the pawn here, it would capture here, and so on, and then we put our pawn here, and it captures here, and so on. So this is the exact stuff is supposed to be implemented in this video. So by the end of this video, we'll have a two-dimensional array representing the pawn attacks for both black pawns and white pawns, and we'll be able to answer the question where the current, like what kind of squares are attacked by the pawn that is set up on a specific given square. So every square, like say pawn on square A1, well, it depends on board in the end, but still, let's say we reference what squares would be attacked if the pawn is on A1. So we'll have this B2 in return, so things like that. And now let me just try to close my arena and open my source file here. So I'm reusing some pre-coded stuff from, well, not even from the previous part, but from the part of 2 videos ago. So let me just quickly walk through this. So we have the definition of unsigned long time as shortly as U64. We have the most essential bit manipulation macros to get, set, and pop the bits. We have our squares mapped, and it's needed to initialize the bitboard easily by just specifying the square instead of calculating the index. And also a very nice handy function here, we can just print our bitboard as it was a chessboard, so A to A table with zeros representing the empty bits and ones representing the bits that are actually turned on. So that's kind of it, very simple stuff here. And before actually going for defining our attacks array, well, we can actually define this, but first we'll need to create a function that would be masking the attacks, and only then we would be actually initializing this array. But let's define the pawn attacks array here. So I can say U64, and U64 means unsigned long, and let's call this pawn attacks. So two-dimensional array where the first element would be side to move, so either black or white, and here we'll have an attack bitboard that corresponds, well, actually let's call this just bitboard like this. So the second part would store the bitboard responsible for the attacks for the square that is set up on a current given index. So, and this would be this would be 2 because we have only 2 sides, like white and black, and here we will have 64 because we have 64 squares on chessboard. So whatever index we use this index would be responsible for the attacks if the pawn is located on the current given square. Okay, and now we need to mask pawn attacks, and this is the actual driver that we would be using in order to actually generate this attacks. So again, like, it's far easier to show rather than to explain, so let me just try to write some code. So U64, and let's call this function mask pawn attacks. Okay, and oh my god, let me think if it is gonna be taking some arguments. Well, let's keep it like this for now. Okay. Oh yeah, it should take the side, so integer side, and also, yeah, obviously integer square. So we would be specifying what square the current pawn is actually located and which side to move. Okay, and now we need to initialize. So we'll need to initialize our attack bitboard, and let's make it this bitboard would serve as a result that we would be returning back from this function. So u64, let's call this attack, and this, so let's initialize this equals to 0, and also we'll need another bitboard to, let's just call this u64 bitboard, and this is needed. Oh my god, how can I explain this, why this is needed for? So we'll be using this to serve as a bitboard where the piece is supposed to be set up. So say we have this square represents where the pawn in our case is actually located. So let's call this piece bitboard. I guess this would be nice. Now we need to set piece on bitboard, and by bitboard I'm bearing in mind this one, so we can simply say like set bit, and we're using this bitboard, and the square serves as the square to where we're supposed to be setting this bit up. And before anything else, I just want to actually run this mask on attacks just to show you visually everything that I'm doing here. And let's say the side would be equal to okay, I don't have the enumeration for sides. Well, let's say white would be equals to 0 and black equals to 1. So we can actually implement that. But yeah, let's just say that 0 would be equal would be responsible for the white pieces to move, and 1 for black pieces to move. I can actually add this enumeration here. Let's say define sides, and I can simply say enum, oh my god, like this, and white and black. In this case, white would be equal to 0 and black would be equal to 1. So now we can say like white, okay, and here let's put this pawn say on e2, okay, and here I just want to print bitboard and this bitboard here. Okay, now I just need to open the terminal, the current working directory, and by typing gcc bitboard .c-o bitboard, and if it compiles, I want to run this executable bitboard file. Okay, it's probably missed. Okay, probably I've missed, yeah, semicolon here. Okay, let's try again. Oh, hold on a sec. Okay, so just as expected, so we did set up our pawn on e2 square. So this is the bitboard responsible for like where the pawn actually is set. That's kind of it. And we don't do yet we don't do anything with our attack bitboards, just to make sure that we have this the square, which represents that the pawn is actually available in this square, and we're setting the bit where the square is regarding the square that is given to us within our masked pawn attacks function. Okay, and now the most important side, the most important part. So depending on side to move, we want to actually initialize our attacks. So let's say if not side, which means if white piece is to move, right? Because white is equal to 0, right? And black is equal to 1. So if not side, this would be one case, and else this would be the case for black. So here we say like white pawn attacks, and here we have black pawn attacks. Okay, and before anything else, I just want to, let's call this initialize attack, or how to call this, setup attack. Okay, I will provide the commentaries later. For now, I just want to say attack. No, not like this. I need to set bit on the attack bitboards, and I want to do this in the square. No, sorry, what am I doing? Not like this. I need to say attack equals attack bitwise OR with the expression of bitboard, and we want to shift the bit that is responsible for the pawn that is currently expected to be on the board to the given offset. So we have the 7 offset for one capture and a set of 9 for another capture. So here, say we have 7, and here 9, or on the contrary, depending on the board and the anise, which doesn't really matter that much at the moment. So I just want, okay, sidewise, so it should generate pieces for it, just should generate white pieces. Okay, and I just want to print bitboard again, like the bitboard that contains the piece, and also print bitboard with the attacks. So let's have a look. Okay, attack. Let's call this attacks. Okay, so yeah, it actually it attacks slightly to the wrong dimension, to the wrong oh my god, direction. So we need to do this like this. Okay, so now we have, also it would be better to replace them to visually represent this in a better way. So here we have a pawn, and here one square upwards and one square to the right is one available attack. Okay, and also, so by the way, the shorter way of rewriting this expression would be like this. So bitwise OR equals, it's the shorter way, and another consideration would be the same, but shift this to 9 squares like that, so to 9 indexes within this bits, 9 bits, right shift 9 bits. Okay, so assuming the current board and the anise, we need to right shift in order to capture white pawns, and respectively we will need to left shift at the same offsets to get the text for the black pawns. But let's actually deal with the white pawns first. So here we have the pawn, the initial pawn, and here we have the attack offsets that are actually available here. But it's not really that easy, because I just want to show you one little thing here. So let me just get rid of this attacks first, and the problem is that it's how it actually to define the off-board captures. And first, before that, I just want to show you how the off-board capture is supposed to be executed at this moment. So it's definitely wrong how it's gonna be, but I just want to show you the idea and then of what's wrong, and then we'll go for implementing like how to fix this. So let's try to put our pawn not to e2 but say on f2. Let's say like this. So now the pawn is here and attack is still on board. So this is fine. Now let's try to place this on g2. Okay. So now it's here and attack is still on board, which is correct. But if we just put our pawn on h1, then a little disaster is going to happen. So let me just demonstrate you this. So if we just yeah, so you see, like we did place our pawn on h1 and it attacks right over in here, which is horribly wrong. And that means that we need to that whatever. So if we just put the pawn, say, not to h2 but to h3 respectively, it would be this like. So you see, it goes on the other side of the board because obviously from the computer perspective it's not a two-dimensional kind of array. So it's a one-dimensional set of bits, and the offset is calculated exactly like we're shifting seven bits to the right. And this is exactly what is happening. So here is our bit, and now we're shifting 7 to the left, to the right. It just visually it's different, but from the computer perspective, it actually shifts to the right. I'm just putting the board this way, but it doesn't matter. So we have 1, 2, 3, 4, 5, 6, and 7, and here we have our bits. So obviously this is kind of wrong. So the idea is that we also we need to make sure that so we need to generate this attack. This attack is to be generated only in case if so now we'll create an additional data structure and an additional bitboard to take care of it. So we'll create a bitboard where we will have all the ones everywhere but on the A file. And what happens if we just bitwise end it with this possibly available bitboard? It would give us well, okay, let me just better to create a variable first, and then okay, so here I want to create not a file bitboard, and now you'll see what I mean by saying this. So let's say for int file equals 0, file less than 8, and file, oh sorry, not we need to start with the rank, sorry. So for rank, int rank equals 0, rank is less than 8, is less than 8, and rank plus plus. Okay, and let's create the bitboard not a file bitboard. We'll first create it locally and then we'll make it global for some reason. So let's call this not a file equals, so let's initialize this as 0 unsigned lone first, like this. Okay, and here, so we need to initialize the square. That would be equal rank multiplied by 8 plus file. Okay, and now we need to say set bit and not a file and the square. But if we do this like so, we will have, let's print bitboard and not a file. So now it would print all the ones. Oh my god. Excuse me. Oh, rank. Yeah, if you're coding in Python too long, you're completely forgetting to put the semicolons and the data types. Sorry for this, guys. So here we have our bitboard initialized with all ones, but we need this A file bits to be equal to 0. So if we just add a condition here, so if we say if not file, or hold on a sec. So if not file is if file is not equal to 0, yeah, this should work. Let me quickly check this. Oh, a bit wrong. So if file, so if any but not 0, yeah. So if file is equal 1, 2, 3, 4, 5, 6, 7, but not the 0, right? So in this case, we just want to set bit. And this is the visual representation of the bitboard that we call not a file. And also it has a decimal representation, but the problem is that it's now printed as signed, even though we have the unsigned lon, but when we print the bitboard, it's a little bit of an issue here. So I just want to say this lon unsigned like this, and now it should print. Yeah, so this D stands for decimal, so just ignore it, and this is the unsigned decimal representation of this sort of a bitboard. And now, guys, I just want to ask you a little question. So what happens if we bitwise AND our not a file bitboard with let me just probably call my yeah, mask points. Okay. Okay. Hold on a sec. Yeah, so I just don't want to print this initial bitboard. Or I can even say, okay, maybe just not printing the attacks, but here I print this bitboard with shifted to 7. Let's for some reason make it like this. Okay, so now this is the potential bitboard that potentially might be representing the attack for a pawn. But as far as we know that this is a matter of offset 7, which means it captures to the right, and we know that if it captures to the right, it can kind of capture to the left, right? So if we have this bit on the A file, this means that it has captured off board. Again, like if we just print this bitboard without this shift, but just the bare bitboard itself, then we'll see, like, so originally pawn is h3. Is this on h3? Yeah, it's on h3. Okay, it's on h3. So initially this is on h3, and we assume that shift to the 7 means it's supposed to be capturing on the right, but eventually we see that it captures actually on the A file, which is definitely wrong. So this bitboard, the bitboard containing the piece shifted, right shifted with a 7-bit indexes, results 1 on the A file. So in order to answer the simple question whether this move is legal or not, we need to bitwise AND this potential attack with our not A file, and it would return us it would actually return us 0. So oh man, I don't know how to explain this. Oh, okay, so if we bitwise AND this to bitboards, it would return us a 0, and well, instead of just writing the implementation up, would probably like to let me just probably try to show you this visually. So we can use this number and this number because they kind of do represent this sort of a bitboards, So I will just store them separately, or maybe even, okay, I just to be honest, I didn't try this before, but let me try now. So printf, I've been implementing this several times, but I've never been explaining this. So this would be the result of lon unsigned decimal. Let's have a new line, and here I will use these numbers. So I will use this number, copy, paste, and this is unsigned lon, and I just want to bitwise AND this with this number, okay, which is also unsigned lon, and it should give us a 0. So let's call this kind of off board, or better to call this on board condition. And you see, like, on board equals 0, and this means like decimal numbers, so it means 0, which means that if it was 1, it would be kind of true, it is on board. If it is 0, it's false, it's not on the board, it's on the A file, and this returns 0 because bitwise ending 1 with 0 here would return 0, and bitwise ending all these ones with all these zeros would be zeros in return as well. So if we just do the same, but let's say we want to put our pawn to, oh my god, let's put it to G3. Okay, and in this case this is the number, so copy, and now all these zeros would result 0, but this one bitwise ended with this one would return 1. It might not be 1, but it returns true anyway. So let me just try to bitwise end this number with paste, save. It would be a non-zero value, yeah. So it's non-zero value, it means true, doesn't matter what value it is, it means true. So if we just do this this stuff conditionally, then if the expression returns true, it means that the attack is on board. Oh my god, guys, this is so hard to explain, to be honest, especially bearing in mind that I'm in Code Monkey King, that a guy who used to just do stuff, monkey see, monkey do principle, and like there is an understanding like how to apply things, but it's incredibly hard for me to understand to explain this. So how we can make use of this sort of a stuff here, the following ways. We can say if, like, let's say make sure attack is on board. So here we can simply say if, and now what we have been doing here within our print statement. So we need to bitwise and our bitboard shifted by paste. And I just wondered regarding some sort of optimization. So I'm going to avoid doing this twice. Yeah, we could have actually stored this in the variable, call it kind of like potential attack, but okay, I'm not gonna be overcomplicating things. So we have this potential attack square, and we need to bitwise end this with not a file, and now let's also make this not a file global, and don't forget to use the value for not a file. So copy, I will just hard code this value to not a file, just for you guys to bear in mind that this is how the not a file, this sort of a constant, looks like in binary representation. So not a file u64, not a file equals to this value unsigned lon. Okay, and I just want to explain this once, because when we will go for implementing the knights and kings, I won't be explaining this again. So I just explained this once and forever in this post. Well, maybe not once and forever, but at least I'm sorry guys. Okay, so not a file bitboard. Okay, not a file bitboard. And again, like, just to give you an idea of how it looks like, I will just now grab this and to give you an idea of how it looks like actually. So paste. So this is how it looks like. Or even, hold on a sec, I just can actually leave this just to give it even more sense. So A, B, C, D, E, G, H. So not a file. Hope now this is pretty clear what it meant here. Okay, so we got this not a file, and now we will be assigning this a tags. So make it like this, or yeah, let's maybe drop back. So now if we just print, so we don't need to print not a file anymore. I just want to comment this stuff out, because for a while we don't really need this. Mask pawns and okay, just print the attacks and that's it. So now we have our pawn on G3, and here it attacks to H4. But if now we just put this pawn on H3, it won't produce any attacks at all. You see, like, no attacks, because the place where exactly this pawn is supposed to be attacking, so this is just it meant kind of off board, so this condition is not passed, so this expression has returned false, this expression. And that's the reason this setting up the bits on the attack bitboards didn't occur, basically. So now we need to do exactly the same thing, but for the opposite direction of the captures. So like right over in here, if I just uncomment this part, you see it still captures to the left, right? But if we just try to put this pawn, let's put this first on, say, B3. Okay, let's put this on B3, save. And now we'll put this on A3. So for now, it's still just, oh, it already prints the both attacks, which is good. So, but if we just now put this to A3, you see what a disaster is gonna happen again. Literally the same stuff here. So you see, like, it captures, so from A3, it captures now to the H file. And this is literally wrong. So we need to do the same we've done here, but instead of bitwise ending with the not a file, we need it to bitwise end it with not h file. So I will now create this not h file variable here. So not a file. Now we'll create a not h file bitboard, and yeah, I will provide the visual binary representation for this as well. But first, let's define this. So U64 not h file, and now we need to, well, let's first make it. Oh, it would be initialized to 0 because this is the global variable, so we can leave it just as is. Now we try to create the not h file bitboard here. So I want to print bitboard not h file. And by the way, guys, I'm not the guy who has created this. I will show you this in the Wikipedia and it's in chess program in Wikipedia basically. So okay, so this is all this stuff is available in chess program in Wikipedia. So all this stuff that I've been showing you guys, and this not A file, not H file, so all this is been explained here. But for me, when I was a beginner, when I just started with bitboard, this wasn't really that trivial to understand. So I would really like to have some more extended explanations like those I'm trying to provide in this video. So anyway, let's get back. So now we need to set bit to not H file and square, and the condition would be a bit different. So if okay, if file so is not equal oh my god, okay, it's not equal to 7. I'm not sure. Okay, yeah. Oh man. So if file is not equal to 7, yeah, so we do this every time when file is not equal to 7, but if the file is equal to 7, which means the 8th the 8th, so we're starting from the index of 0. That's why the biggest value for the file would be 7, not 8. If we started with 1, it would be actually 8, but then we need to say less equals than 8, but forget that. So the idea is, well, let's just drop it. So the idea is just to have this like format. So we have this H file being considered as, so we have 0, 0. So let me just copy this and paste this back to right over in here, and again A, B, C, D, E, F, G, H, save. And now here we can simply say again, like, make sure attack is on board, and we say if and the bitboard shifted to the 9 indexes to the right, bitwise ended with not H file. Only in this case we want to update our attacks. Okay, so I really hope, so probably we don't need this stuff anymore. Okay. Okay, mask point attacks A3. So okay, let's go to B3 back, and let's try to print this. Okay, hold on a sec. What have I done? I forgot to initialize this globally. So I need this value. Okay. Otherwise, obviously, it won't be working. And paste it here. Unsigned loan. Oh my god. Unsigned loan. 471 is the. Okay. And. Okay. And don't print this anymore. So now we have the pawn on B3. It attacks both sides, but if we just try to put this to A3 now, in this case, okay, it's on A3, and it only attacks to B4, and it doesn't overlap to the H file. So this is actually the concept I was trying to give you an idea, guys. So now we need to make exactly the same thing, but for the black pawns. So in order to do this, we need to make a very simple stuff here. So for black pieces, bearing in mind the opposite bit shift, it would be literally the same, but with some minor differences here. So this. So we just switch the shifts to the left, and probably we need to replace these guys with their places. It should work, but obviously still I need to check this out. So let's try to attack with the black pieces, and let's put it on B3. Save. Now hold my breath. Okay, so it's now on B3, so the attacks are going to A2 and C2. Okay, and now I just try to put it on A3, and I hope that it's not gonna be overlapping anywhere. Okay, and it doesn't. So yeah, so not H file, right? And yeah, so it only goes here. And is it? Yeah, it is. So here is the pawn, and here is the attack. Okay, and now let's go to G3. So we got our pawn on G3, and here are the attacks on F2 and H2. And now we just put it on H3. It should only attack the G2 and not overlap anywhere else. So H3. Okay. H3, yeah, now it attacks only to G2 and doesn't go to A file anymore. Oh my god, guys, perfect. So we've finally managed to create our pawn mask attacks function. So the very last thing left here is actually trying to initialize this sort of an array responsible for responsible for generating this like attack maps. So let me just put a pawn somewhere on, I don't know, let's make it for white, say, and let's put it on, say, E4. Save, run. I also don't want to, oh yeah, just one more little trick here. So instead of printing things here, we need now to return our attack. So here we just return attack map for a pawn on a given square, like this. And from now on, this pawn attack masks function would return a bitboard containing the appropriate attacks. So we just say, like, let's call this U64. This is E4, right? White E4 attacks equals, and now we can just, okay, I don't need, well, I'm not gonna be deleting this stuff, because we'll need to make use of it in the next videos for generating not some sort of a files for knight attacks and king attacks, but that would be covered a little bit later on. So I mean in the next videos. So now we need just to printf and oh no, we just, you know, it's enough to print the bitboard. So here I can simply say the new line here, and now just print bitboard and this stuff, and it now should print what? Attacks. Okay, perfect. So attacks for white pawn on E4, and this is what we got here. So it attacks the D5 square, yeah, and the F5 square, like this. And now we need to, so this is now this is the only attack map just for a white pawn in the only square of E4. But we need to generate this like attacks for pawns on all the available squares. So in order to do this, so first I will do it probably, or I will now start, okay, pawn attacks, not h file. I will now start. So let's say initialize pre-calculated attack tables for leaper pieces. Leaper pieces means pawns, knights, and kings, while the slider pieces means the rooks, queens, and bishops. Okay, so let's create, I guess this might be a wait function, and let's call this init leaper attacks. Okay, and here we need to loop over 64 board squares. So very simple. So for int square equals 64 square. Oh my god, what have I done? Equals 0. Square is less than 64 and square plus plus. And here, so first we need to initialize white pawn attacks. So now we need to reference our white pawn attacks. So pawn attacks, copy pawn attacks, and for white pieces, which means the index of 0, and here we index this by the square, and it would be equal to pawn mask, mask pawn attacks, mask pawn attacks, and white, right, and the square. And now the same for black pawns. Let's say init pawn attacks. So I hope this would be quite pretty self-explanatory that we're doing this for both white and black pieces. So here we do the same but for the black pieces, and masking the black pawn attacks. Save. Okay, so it now should actually kind of work, but I still want to, well, probably I will create this in the next video one more time, so just drop it. So here let's print white pawn attacks, and so we can say for int square equals 0. So this is just a driver to check our logic if it's working correctly or not. So squares less than 64, square plus plus. And here we just want to print the bitboard print bitboard pawn attacks, and side to move, let's make it white. Okay, and for a current given square. Okay guys, now hold my breath and try to run this stuff. I hope I will have the pre-calculated attacks. So just let me just clear the console and run this again, so just can scroll totally upwards. Okay, so for pawns on, okay, so they all seem so. Something has gone horribly wrong. I can't see them getting initialized. Okay, guys, just hold on a sec. I need to figure out what's gonna run here. Oh my god, guys, I just forgot to initialize my Leaper attacks function here. How could I done this? Okay, initialize Leaper attacks. Oh man. Oh god, yeah. Yeah, obviously I need to initialize them. Otherwise this code doesn't work for sure. Okay, so now I really hope this should actually print this attacks. Okay, so let me just clear my screen again and run this one more time. So yeah, I was doing like I did something wrong there. Okay, so if the pawn is, I'm not sure, probably pawns are if they are here. White pawns, yeah, they're not doing anything. This is right. Okay. Okay, now pawn stands on a7 and attacks only to b8. Okay, now pawn stands here and attacks already a8 and c8. Okay, so we're shifting the pawn, shifting the pawn, shifting the pawn, shifting the pawn. Okay, no overlaps. Okay, now it's here and attacks here. Now it's here, attacks here. Okay, so it seems to be quite pretty nicely here. Okay, and again. So as far as I've already been doing this before actually recording this video on the new bitboard chess engine I'm currently working on, I can say with a 99% sure that this works correctly. And yeah, and the very last position here. Okay, so now we can do the same but for black pawns as well. So print actually black pawn attacks. So let's just get rid of this part, or probably I will leave this code just for clarity purposes. So here we just want to print the black pawn attacks. I will only now comment this out for a while just to easily just to get them easier. Forget that. Okay, so okay, yeah. Now if pawn was here, obviously it's impossible, but from the pre-calculated attack tables, now pawn is here. This is possible. Okay, if pawn is here. Okay. Yeah, now pawn is here. Now pawn is here, attacks downside, downwards. Pawn is here, attacks downwards, attacks. Okay, and eventually comes to, so if pawn is here, it's not attacking anything there. And yeah, so now we have pawn here. Now we have pawn here and here. Yeah, this seems to be working quite pretty nicely. Well, okay guys, so I guess this is it for this tutorial, and I really hope that you've learned something interesting out of it, out of watching it, or if you have been following this I appreciate it so much, because all this stuff is very practical, and there is I can't see much sense in just watching this without trying this at home, basically, because it's incredibly addicting and interesting thing to consider. Chess programming is very addicting. So now a little teaser regarding the future couple of videos. So I'm not gonna be in the next couple of videos, I mean even in the next more than couple of videos, I'm not gonna be explaining how exactly we can make use of these pre-calculated attack tables, because it needs some particular applications to show there, like implementing the each square attack function, or some patterns regarding the mode generation. And obviously I'm not going to be going through all the possible mode generation ideas, like those that have the double pawns and castling moves. That I will leave this for you as an exercise, but some very basics regarding how to generate the moves based on the captures. I mean, not on the captures, but but those moves that can make use of this generated of this attack tables would definitely be covered, and that would be very interesting. So we'll need to have some additional stuff, like bearing in mind the idea that there might be either your own piece or the opponent's piece on the chessboard. So that would involve two additional occupancy bitboards that represent all the white pieces or all the black pieces to make some bitwise end operations between these attacks and those occupancy bitboards. But this would be covered later on. The next couple of videos I'm going to be doing the same that we've done already with pawns, but with the knights and the kings, the rest of the two leaper pieces left there. So it would be slightly more difficult for knights because well, actually in terms of code this would be almost like the same, but we need more than one file to bitwise end our offset that would be responsible for the potential attack available, because knight has a bigger offset, so it can overlap not the one file but two files, and in some cases even 3 files. So that would be covered as well. And king is much like the pawn, but again it just needs to it needs slightly bit different implementation, obviously. But anyway, the idea of generating pre-calculated attacks for leaper pieces is all about the same, and making use of these pre-calculated attack tables during the mode generation process, as well as the implementing the square attack function, they all are literally the same. But when it comes to the slider pieces, that is going to be really interesting, because generating the attacks for sliding pieces is a real challenge. And as I was already mentioned, there were lots of discussions on Talk Chess forum regarding how in particular to generate those attacks, and that's I can talk about that endlessly, I guess. So probably I will make some chess programming blog video covering this topic, highlighting this topic at least. So something like that. Well, okay guys, so now this is really it for this video. I appreciate if you watch this entirely, and even more if you try to follow this tutorial. Please feel free to ask your questions in the commentary section below this video. If you didn't get some concepts being presented in this video, basically. And this is it from my side. I wish you all the best until the next time, and take care.